All right, cool. Thanks for coming out. This PUNLAG talk is on the fast Fourier transform. It goes along with our theme of looking at fast matrix vector product operations. And it segues kind of nicely into, we're going to talk a good deal about eigenvalues, and I hope to pick up with this talk next time and look at eigenvalues of certain structured matrices using some of this theory. Cool. So, fast Fourier transform, or in its matrix variant discrete Fourier transform, I'll use the terms interchangeably, even though they're not actually the same thing. But this has a lot of applications in, I am told, signal processing and just a lot of structured matrices that come up in applied math problems. I don't know a whole lot about those. I just know and am told that this is used in a lot of places. So I'll give a little bit more application discussion later on once I've got some concrete examples in front of us. So to develop this idea, we have to talk first about roots of unity. So I'm going to use W sub n to denote a primitive nth root of unity. Primitive meaning it generates all of the other nth roots of unity. And so if you remember the famous e to the 2 pi I equals 1 statement, so if you divide this, if you take the nth root of this thing on the left side, then you get an nth root of unity on the right-hand side. And there are n different roots of, there are n different nth roots of unity. We just raise W sub n to the power j, and that the actual symbolic expression for that is j over n as a exponent in this expression. And so these have some pretty neat properties that we're going to exploit today for fast matvec. In particular, right now it is enough to know that all of them are roots of the polynomial x to the n minus 1. And that's because any of these, if you raise to the nth power, you're really raising this to the nth power. And when you do that, exponent multiplies by other exponents. So j over n times n is just 2 pi I times j. This is just an integer. And so we're really just looking at an integer power of 1. And so all of these roots of unity satisfy this polynomial. Another kind of cool thing is if you have the jth power of a root, an nth root of unity, and you take the conjugate, well, that's equal to taking the conjugate of this. But when you take the conjugate of something of this form, it's really just introducing a minus sign in the exponent. And so this is really just equal to, you put a minus sign in front of this, and that is really equal to the nth root of unity raised to the negative j power. And last thing, if p is some integer that divides n, then we have that raising the nth root of unity to the power p gives us a different primitive root of unity. We can think of, since p divides n, let's say it's 3 and 15, you can think of that as 1/5. And so down here, that translates into 1 over n divided by p. This fraction and this fraction are really the same. But this thing down here is the n divided by pth root of unity. And this generates all of the n divided by pth roots of unity. So those are all facts that we're going to use later on in this talk. All right, so this part in particular I want to focus on now, and the connection to some things I mentioned in a talk at the beginning of the semester. We're going to look at a Vandermonde matrix, which I remind you is a kind of Krylov matrix. And specifically, we're going to use the relationship that Vandermonde matrices have to a companion matrix. So, first, let's let W sub n be the diagonal matrix with the roots of unity, the nth roots of unity on the diagonal. So as an example, the fourth root of unity is I, and so W sub 4 is equal to, well, I raised to the 0th power is 1, I raised to the 1th power is I squared is -1, and I to the 3rd power is -I. Okay. Then, remind you, a Krylov matrix for a matrix and an input vector is you just take all the powers of your matrix A times your vector. So we are specifically going to use the Krylov matrix with this roots of unity matrix W. We're going to look at, and I'm going to call it F temporarily. I'll say why in a bit. We're going to look at the Krylov matrix generated with the roots of unity on the diagonal, and E, the vector of all ones. So I use E vector to be the vector of all ones. What does that really look like? You've got all ones in the left-hand column because a Krylov matrix starts with just the vector. Then the next column is the roots of unity times this vector. So that means we're just going to have the nth root of unity to the 0th power, nth root of unity to the 1st power, nth root of unity to the 2nd power, all the way down to the n minus 1th power. Then the next vector over is this vector times the roots of unity. So this times the 0th root of unity is again that. This is now that times itself, so we're adding 1. And to make a long story short, really what this matrix looks like, if you take the jkth entry, it's the nth root of unity raised to the j minus 1th power times the k minus 1th power. So column k gives you a power, and row j also gives you a power. In particular, if you're in the first row or the first column, then this is going to be 0. So you have 1s here and 1s here. And that's why the matrix looks that way. So I use the letter F because I'm going to call this the Fourier matrix. Just as an example, F sub 4 would be 1, 1, 1, 1, 1, 1, 1. Okay, and now here we would want I to the row 2, column 2. So this is 2 minus 1, 2 minus 1 is the exponent because we're using j minus 1 times k minus 1. And that is, this is 1, so this is I. So I goes there. And then the exponent here is 3 minus 1 times 2 minus 1, that is 2. So I squared is -1. And then same thing happens up here. And then -I here, -I up here. Note that the matrix has to be symmetric because if you interchange j and k here, then you're just interchanging j and k here. But that doesn't change what this number is. So this value stays the same. So we know that it's symmetric. Okay, what is this entry? Both powers are 3. So 3 minus 1 is 2 times 2 is 4. I to the 4th power is simply 1. I to the 4th power is 1. Here we would have 4 minus 1 and 3 minus 1. And that is 3 times 2 is 6 is the power. What's I to the 6th power? Negative 1. And then this must be negative 1. And then both of these are 4. This would be 3. This would be 3. So that's 9. What is I to the 9th power? That is I, right? I. Yeah, okay, cool. So it is symmetric. What other properties do we have? F is symmetric. And even more importantly, how do I want to phrase this so it's easier to prove? This is its most important property. It's not quite unitary, but it almost is unitary. When you multiply Fn by its own conjugate transpose, you get n times the identity. And what that means is if we define un, I'm going to define this a particular way so that some algebra works out easily later on. Define un to be square root 1 over square root n times the conjugate of Fn. Okay, and that means that the conjugate transpose of un is simply Fn. There we go. Okay, so now I have some things to prove. First, I mentioned back here that I was going to use some connections of, first, the fact that a Krylov matrix in this setting is really a Vandermonde matrix, and then a relationship of a Vandermonde matrix to a companion matrix. That's on hold for the moment. We will get to that. Right now, I want to justify this claim, and then we will get back to discussing the Fourier matrix as a Vandermonde matrix and its relationship to a companion matrix. Okay, so with that definition, now we want to prove this claim. Proof that this is true. If you look at row j here, so let's look at entry jk of this equation. So entry jk I need more space. On the right-hand side, the jkth entry is either 0 or it's n. We'll consider both cases. On the left-hand side, we have row j of this inner product with column k of this. Well, since Fn is symmetric, row j is really just equal to column k of Fn, but then we do have to take the conjugate. Column k is a bit easier. Let's just look at column k. Column k looks like this. We're using nth roots of unity, and the exponent should be j minus 1 times k minus 1. K is fixed, so all the exponents are going to have k minus 1 as a factor. And then j minus 1 is 0 here. Then j minus 1 is 1 here. Then j minus 1 is 2 here. And all the way down to j minus 1 is n minus 1 here. Cool. Row j of this is going to be the conjugate of column j. So it's going to look like this, except with j's here, and then we're going to take the conjugate. So conjugate, so j minus 1, and then take the conjugate of the whole thing, all the way out to nth root of unity, n minus 1, j minus 1, take the conjugate. Then now we use one of the facts about roots of unity I mentioned earlier on, that taking the conjugate is really just putting a minus sign there. Dot product with the same vector up here. Okay, so when we actually perform this inner product, we get the summation of this thing times this thing, right? So nth root of unity minus L L, I'm gonna denote this number by L. So L goes from 0 up to n minus 1. And then L is multiplied by j minus 1. And we have a minus sign in front of it. This times, it gets multiplied by same root of unity, still L, and then k minus 1 is a factor. And there's no minus sign in this exponent, whereas there is a minus sign here. We have the same base here, so we can just add exponents. So this is equal to, just to recap, we are looking at entry jk of this matrix. And we've shown it's equal to the sum as L goes from 0 to n minus 1 of root of unity n L times k minus 1 minus L times j minus 1. We can factor out L here. And then we can note that k minus 1 minus j minus 1 is really k minus j. This is fixed. It's a constant. Same thing with this. So we can look at this as follows, where y is equal to the nth root of unity raised to the k minus j power. Since this whole thing is a constant with respect to L, just think of it as one thing. Okay, now we can move on to cases. In the case that k equals j, this is 0, so this is 1, so y is 1. One to the L is just 1. There are n different terms in the sum, so we get n. And this proves that the diagonal of this matrix is, in fact, what we want it to be. Okay. If k is not equal to j, then the only thing that really matters is that if k is not equal to j, we get some complex number that is not 1. Because it's not 1, we can use a really neat identity to simplify this. This looks a little bit like a partial geometric series. It is a partial geometric series. So we can use the fact that I need a little bit more space. So summation from L equals 0 to n minus 1 is equal to 1 minus y to the n over 1 minus y. Since 1 is not equal to y, this is not 0, and so this expression is well defined. And so we know that this expression holds. Cool thing here is, what is y? Y is this. This is an nth root of unity still. When we raise y to the nth power, this becomes 1. So this is 1. So this is 0. So this thing is 0. So that's a quick proof that a Fourier matrix times its conjugate transpose really does give us n times I. And then dividing by n and splitting n up into square root n in the denominator of each of these matrices gives us that un is a unitary version, a unitary scaling of the Fourier matrix. Okay. So now that we've got that out of the way, what are we going to do with it? All right. Now we get back to Krylov matrix, Vandermonde matrix, companion matrix. So Fn is a Vandermonde matrix. Vandermonde matrices satisfy the following. Vandermonde matrices satisfy this equation for V, the Vandermonde matrix with respect to the roots of the polynomial P for which C is the companion matrix. For which C is the companion matrix, and roots for which lambda has the roots on the diagonal. So lambda is a diagonal matrix with some values on the diagonal. Take those values to be the roots of a polynomial. That polynomial has this companion matrix. Then the Vandermonde matrix with the Vandermonde matrix taken with respect to those roots satisfies this equation. So in our particular situation, Fn is the Vandermonde matrix in question. The roots is the diagonal matrix of the roots of unity. And the companion matrix is for the polynomial that has these roots, these values as its roots. C has exactly this polynomial. C is the companion matrix for this polynomial, since W is the diagonal matrix with the roots of unity on its diagonal. And these roots of unity satisfy exactly this polynomial. Okay, so we know that this is true. Well, since Fn, since the Fourier matrix is invertible, we can convert this equation to something kind of nifty. If we divide both sides by square root n, then we end up with this, and in particular, this, which is kind of cool. It's even cooler when we actually look at the companion matrix. The companion matrix is highly structured. So in general, a companion matrix looks like this. For some polynomial coefficients here, but for us, because our polynomial has no coefficients, more or less, except this one, our specific companion matrix, the one we're looking at, is this, with ones on the subdiagonal and then a 1 in the upper right-hand corner. So I sort of draw it shorthand as a box with a line just under the diagonal and then 1 up in the corner. This is super cool because it's a permutation matrix. It's a Hessenberg matrix, but that doesn't really matter. This turns out to also be a Krylov matrix. And in particular right now, I think of it as a downshift permutation or as a so-called circulant permutation. And this is sort of a centerpiece or a building block of circulant matrices, which is what we're going to get to next. Okay. So now we define a circulant matrix, and we're going to make use of this. And the reason I bothered to develop this relationship is because this is going to allow us to use the Fourier matrix and roots of unity to do quick operations with things that are composed of this circulant matrix. That's where we're headed. Okay. Circulant matrix are taken with respect to a vector B, looks like this. B0, B1, Bn minus 1, You know what, I'm just going to say it's m. I'm going to say it's m plus 1 by m plus 1, so I don't have to write m minus 1. The circulant matrix RB looks like this. You just take that vector and put it in the first column. Then the idea is you take the vector and you shift every entry down 1, take the last one and move it to the top. Another way you can think of it is every diagonal, the diagonal is constant. So the whole diagonal, because you shift the vector down each time, B0 goes down when you go over one column. So B0 is the main diagonal the whole way. B1 is the subdiagonal the whole way until it gets here when it wraps around to the top. BM starts here. Now BM starts here, and then it goes to the top, and then it's on the super diagonal the whole way down. There, that's enough information. One way you can think of this, one way I like to think of it for some theoretical properties, is as the Krylov matrix of the circulant shift permutation. So I think of it as the downshift permutation or the circulant permutation. And your vector B. So this first vector B is the first column of our circulant matrix. Then to get the next column, you shift everything down by 1 by multiplying B by the downshift permutation. And then the next column you get by shifting the previous vector down 1 spot using the downshift permutation, and so on. So you can think of a circulant matrix taken with respect to any vector. You can think of it as being a Krylov matrix with this downshift permutation C. Or another way you can think of it you can also think of it as a polynomial in this matrix C. You can think of it like this. B, J, J goes from 0 to M times C to the J. So here's our coefficients, and then here are powers of the circulant matrix. The reason this works out is because C0 is the identity. When you multiply C0 by B0, you get B0 on the main diagonal. Cool. When J is equal to 1, you have the circulant matrix times B1. The circulant matrix has 1s on the subdiagonal and then a 1 up here, which is exactly the locations of B1. Every time you multiply C by itself, that just shifts down 1 more diagonal, so that C2 tells us what's on the second diagonal, and then it has a little bit that wraps around up here. And that continues so on all the way up to C to the M, which gives us the coefficients that are here and on the first superdiagonal. So you can think of a circulant matrix both ways. Both have some neat theoretical properties. You can learn neat theoretical properties from both perspectives. I'm going to focus on the Krylov thing just because we've already talked about that in this seminar. All right, that is a lot. Before I get to a big theorem relating all of this business. Any questions? Okay. How much of this have you seen before? I'm curious. Some of it, any of it? Yeah? All right, cool. So the reason circulant matrices are important is because, theorem, the reason we're able to do fast matrix vector products with circulant matrices is because they are built out of the Fourier matrix. So it turns out you can represent any circulant matrix R with respect to some vector, you can think of it as UN times diag Fn times B times UN conjugate transpose. So here is our scaled Fourier matrix. And then we have the eigenvalues of our circulant matrix are easily computed by multiplying that defining vector B by the Fourier matrix. So what this is saying is that the Fourier matrix, in fact, gives all of the orthonormal eigenvectors for the circulant matrix. Circulant matrices all have exactly the same eigenvectors. These are the eigenvectors. The Fourier matrix is exactly the eigenvectors for all circulant matrices. All circulant matrices are diagonalized by the exact same set of eigenvectors, which is pretty powerful. So a fast matrix vector product with a Fourier matrix means we can do this fast. Diagonal times a vector is also fast, and then another Fourier matrix times a vector would also be fast. So doing 3 fast products allows us to multiply a circulant matrix by a vector very, very quickly. So I'm going to prove this, and then I'm going to describe exactly how to do such a matrix vector product quickly. So proof that circulant matrices are diagonalized by the Fourier matrix. All right, so I'm going to conjugate by UN and move things back over. So the statement that I'm going to prove is this. And I'm going to drop superscripts. I'm sorry, I'm going to drop subscripts because it's clear from context. Okay, so I think of R for this proof as a Krylov matrix. And I'm going to left multiply that Krylov matrix by U star. So what is this equal to? Thinking of this in terms of what a Krylov matrix is, we have that. Then I'm going to pass this through and multiply it by every vector. And for each of the matrices C, I'm going to insert a nice form of the identity matrix between the different factors of C and between C and B so that things work out in a nice way. The way it's going to work out is now that every factor of C is surrounded by U transpose U, or U conjugate transpose U, we can use the identity. Do I still have it up? I erased it. We can use the identity that I wrote down earlier, the roots of unity times our Vandermonde matrix is equal to our Vandermonde matrix times the companion matrix. And in our context, the companion matrix is exactly this downshift permutation matrix. Our Vandermonde matrix is exactly this scaled Fourier matrix, and W is the roots of unity. So each of these factors, U, Hermitian, or conjugate transpose, CU, each of those turns into a factor of W. So now this is a different kind of Krylov matrix. It's a Krylov matrix with respect to W, the roots of unity. Okay, now we use another fact about Krylov matrices. So right now what we're dealing with is U transpose Krylov of C and B, we've found so far that's equal to Krylov of W and U transpose B. Looking back here, we can factor out a diagonal matrix that has these entries on the diagonal. The reason we can do that is because each of these matrices W is diagonal. So I need to illustrate that. So I'm claiming let D equal diagonal of U star times B. Then really what we have here U star B. Then really what we have here, everywhere we have this vector, instead I'm going to think of that as the vector of all ones times this diagonal. So I'm just pointing out that instead of thinking of this as a vector, you can think of it as the vector of all ones scaled by the diagonal matrix that has exactly its entries on the diagonal. Okay, why? Because that makes it a little bit easier to see the following. This is the Krylov matrix we're dealing with now. W, I remind you, is a diagonal matrix with the roots of unity on the diagonal. Diagonal matrices commute. That's what I'm getting at here. Diagonal matrices commute. So I can factor D on the left of all the W's. Factor D on the left of all the W's. So that now what are we dealing with? We're dealing with this thing is equal to, I'm factoring D out of the matrix. So now D is on the left-hand side, outside of the matrix. The reason I'm doing all that is because now we can see this is in fact a Vandermonde matrix with the roots of unity. This is exactly how I defined the Fourier matrix. That is exactly what the Fourier matrix is. So we have, this is the original circulant matrix, which we're thinking of as a Krylov matrix. And then on the right-hand side here, we have a different Krylov matrix, which is really a Vandermonde matrix, which is really F sub n, the Fourier matrix, because that's exactly how we defined it. Okay, now I'm going to substitute back in whatever D was. It was U star B. Now we're getting somewhere. Okay. U star, U conjugate transpose is really just, I don't have it written down anymore. It is really just equal to a scaling of Fn. U star is really just equal to 1 over square root n times Fn. Now I'm going to factor this scalar out of the diagonal matrix and multiply it by F. One over square root n times F is really just equal to U star. So now we multiply both sides of the equation by U star, and we have U star circulant matrix. Bringing that over, we get U. There. U star circulant matrix with respect to B, U diagonal matrix with F and B. And that exactly proves the theorem, which I've since erased. Okay, so now we've shown we can decompose a circulant matrix as Fourier matrix, diagonal matrix, Fourier matrix. So now we want to know that we can actually do a fast product with Fourier matrices. I also want to define Toeplitz matrices and Hankel matrices in terms of circulant matrices. but I'm running out of time. So I am gonna get right into the fast matvec. I might have to continue this next week. So fast matvec with the Fourier matrix. And we're going to use some of those relationships between roots of unity that I wrote earlier. Okay, the key idea is that we're going to decompose Fn times a certain permutation. We can decompose that to look something like this. So we start with one full n by n Fourier matrix. You permute things in a special way, and that decomposes into 4 diagonal blocks and then 2 Fourier matrices of half the size. By recurring that, you can only have the size log n times. By recurring that, you end up doing log n different products that are linear time. And since they're linear time, they're times n. And so that's just an intuition for where this runtime comes from. The details that I want to get into are what permutation is this, how does it decompose into these blocks, and then how do we know that this thing is actually a Fourier matrix for roots of unity that are half n of what we started with.